All right, welcome. We're going to do a chapter 5 review test. I just found this online, but here's some solutions. So for this first one, we're going to multiply it out. Maybe I'll just zoom in for us so we could do them sort of one at a time. So this would be equal to the integral. This would be 4x to the fourth plus 4x squared plus 1 dx. And when you integrate that, you get 4x to the fifth over 5 plus 4x cubed over 3 plus x plus an arbitrary constant c. Great. So for this one, you could use u substitution to do the 4x minus 3, and we did this one in class, but we'll see that this will end up giving us a negative cosine of 4x minus 3. But you could think about it this way. If I were to do a derivative of that right-hand side, a 4 would pop out on top. So to counteract that, I have to divide by a 4, and you could verify that that is, in fact, the answer. For number 3, I'm going to bring the constant out in front because it's not needed for the integral in there. And then you see, e to the x just stays the same. So it's 5 e to the x plus an arbitrary constant c. It doesn't actually matter that it would be 5 times that arbitrary constant since it's just an arbitrary constant. Very good. Let's do this. Yellow. Is that an okay color? So for this one, I'm going to do a little bit of prep work. I'm going to say u is equal to what's inside 4 plus x cubed. And that will give me du is equal to 3x squared dx. And so my problem here just becomes the integral of the square root of u du when I substitute everything in there. And so this will give me u to the power of 3 halves times 2/3 plus a constant, and then I just need to substitute back in what we had originally. So it was 4 plus x cubed to the 3 halves plus a constant c. Good, so for this one, I'm going to let my u be the denominator, 8x plus 1, and then du would equal 8 dx. So notice we don't have an 8 in this problem. Some people would prefer to put an 8 in this problem and then divide by 8 out here to make it really like multiplying by 1. That is an okay way of doing it. Or you could solve this right here to get dx by itself. Either way, it'll give you the integral with a 1/8 here. I'll move that out in front of 1 over u du. So that would be the natural log. So 1/8 of the natural log of u plus a constant. And in this case, for the u, we have 8x plus 1, so we just substitute that in there. 8x plus 1 plus a constant. We did this one in class, and we saw that rewriting it as cosine of 2 theta over sine of 2 theta would be very helpful. They have an x there. They really meant d theta. Otherwise, you would treat the function like it was a constant. So in this case, if you let u be what's down below sine of 2 theta, you'd end up with u equals sine 2 theta, a little bit of side work here. Du would equal negative cosine with a 2 theta, and then there's a 2 that pops out of there. D theta. I'm running a little bit tight on space here. Apologies, I feel like Alex Glenn. Oh, shots fired! So in this case, we're going to do our substitutions here, where we're going to end up with a negative 1/2 when I pull that to the other side. And we'd have du and 1 over u. So this then would be negative 1/2 natural log of u, and in this case, oh, I'm sorry, where did that negative come from? Hold the phone, everybody. Sine just goes to cosine. I don't need a negative there. No negative there. Sorry about that. Speed running, you know. It's what we do. Mistakes were made. And the u in this case is sine of 2 theta plus some arbitrary constant. Great. So when I look at a problem like 7, my first thought might be, hey, maybe I can do some u substitution down below. Now, because of that x squared, I'd really need an x up top for that to work, so it just won't work. Now, if I look at my table, I do have something in my table that says if I had the integral of 1 over x squared plus 1, or I might call it 1 plus x squared dx, that would be equal to the inverse tangent of x plus a constant. Let's see if I can get that table to show up on here. Not quite what I want it to look like, but that's over here. So that is from in our section. Now, one thing that we would need to do is we would do a little bit of messing with it to get that form of 1 over x squared plus 1. You know, it's not super important. I doubt I'd ask you this particular one on a test. I could show you how we could massage this a little bit. What we would need to do, I'll do it over here on the left-hand side, is I would say, well, let's go ahead and pull the 4 out in front. And I'd have 1 over 9 plus 4x squared dx. I really just want to get a 1 right there, and then we'll do a u substitution. So I'm going to pull 1/9 out of this as well. So that'll come out in front. So if I pull 9 out of the bottom, that first term is a 1, and this next thing turns into a 4x squared over 9 dx. So notice this right here could be written, I'll bring the 4/9 down, as 1 over 1 plus 2x over 3 squared dx. And that hints to me that if I let u be 2x over 3, then du will be 2/3 dx. Or in other words, 3/2 du would equal dx. And then I can stick that in to my problem, scroll down a tad here, and say this then becomes, 4/9. I'm going to bring the 3/2 along. 1 over 1 plus u squared du, which gives me then, simplifying out in front, the 4 and the 2 give me a 2 up top. 3 and the 9 give me a 3 down below. 2/3 tangent inverse of u, where u is 2x over 3 plus a constant. So it takes a little bit of work, and I could show you at some point. The table in the back of the book is a little bit better, but it's more complicated to allow for u substitution already being accounted for. All right, number 8. Simplify this hot tamale. That would be x plus 1 over x squared dx. Or if you don't like 1 over x squared, you can call it x to the negative 2. So that gives you, when you take it, x squared over 2 minus x to the negative 1 plus a constant. All right, hot dog. Zoom in on these. 9. The 6 is a constant. It comes along for the ride. 9 natural log of x plus a constant. This problem right here, I'm going to let u be x cubed, and then du would be 3x squared. I don't have a 3 here. Well, if I stick one in there and a 1/3 out in front, then I am ready to say it's 1/3 integral of e to the u du, which is 1/3 e to the u, and in this case, u is x cubed. All right, we talked about these ones a little bit in class. I might just draw a little sketch because, hey, this is meant to be instructional. Okay, and then 10. So let's say we have something like this. So we know the area from 0 to 4, this is equal to 7. And we know the area from 4 to 10, all that added up, is equal to negative 3. For the illustration, I could have put it hitting 0 at 4, but it's not necessary, right? Just the whole area from 4 to 10 adds up to negative 3. So what is the entire thing from 0 to 10? Well, that would be the 7 plus the negative 3, so that is 4. Part B. If instead of going from 0 to 4, I went 4 to 0, it just flips the sign, so I get negative 7. The area underneath at the point x equals 5. Well, that's 0. And then part D here, I'll do that in red. We know the first one, this is 0 to 4 of f of x dx. We know that one's equal to 7. But be plus integral from 0 to 4 of 3 dx, which gives me a 3x, plugging in the 0 and the 4, which just gives me 12. So it'd be 7 plus 12, which is 19. All right, now we've got some definite integrals. Maybe I should have done these in two little areas. Oh well, we'll do it. All right, so the definite integral of cosine of x, well, that would be negative sine. Oh, excuse me, I always get those mixed up, don't you? All right, because sine goes to cosine as a derivative, so the integral would be, of cosine would just be sine of x. Plug in pi halves and 0. That's equal to 1 minus 0. So 1. For number 13, right, if my, I can either multiply it out or I could say let u be 1 minus x squared. Du then would be negative 2x dx. So the negative 2, I'm just going to divide that. So it would be negative 1/2 the integral of u cubed du. All right, and I'm going to change these bounds. So if x is negative 1, 1 minus negative 1 squared is 0. And if x is 2, 1 minus 2 squared is negative 3. So this, the negative 1/2 is coming along for the ride. And we're going to do u to the 4th over 4, plugging in negative 3 and 0. When I subtract off the 0, it's going to be nothing. So we're really just looking at the negative 1/2. Excuse me. Plugging in a 3 to the 4th, that would be, what, 81 fourths. All right, so negative 81/8. That's at least what I got. No guarantees these are correct. You guys should check these as well. Let me know if this video is wrong. Again, I'm just doing this in real time. Haven't worked these out before, ever. Let's simplify this one. That's at least what my gut says we should do. I've got a 3x squared. I'm going to pull out an x out of up top here. We've got 3x minus 2. And then I'm going to pull an x squared out from below. And I have an x minus 1 dx. No, actually, this is much easier. Back it up, folks. Guess and check. I just noticed the top is just a derivative of the bottom. So we're just going to let u be x cubed minus x squared. And then du would be 3x squared minus 2x dx. That's way better. So this would be 1 over u du. Now, and when x is 2, that's 8 minus 4 is 4. When x is 5, that's 125 minus 25 to 100. And so then we have the natural log of u from evaluate at 104, right? So this would be natural log of 100 minus natural log of 4. You could also simplify that to the natural log of 25 if you are a happy-go-lucky camper. All right, getting close to time. So this one I can integrate it. I can also recognize it's odd. This is negative. This is positive, so that gives me a 0. This one right here, it's going to be something involving an inverse sign. Just kind of like that tangent, though. It'd be kind of nasty to set it up with our current tools. I haven't shown you the trick yet. So let's not worry about that one at the moment. Let's do number 17. So this one, it's a bit funky, right? Insofar as we have from 2 to negative 2. So you might hope, hey, maybe this is an odd function, maybe it's an even function. It turns out to be neither of those. So that's a bit of the unhappy person, whatever you want to call it. So there is another technique, but it looks like we're at just about a time for this video. So I'm going to do this one as the first one on the next.